Oh, hey, didn't see you there. So it turns out, like most radio amateurs, I'm easily distracted by new projects, new shiny things. You know, do you want to build a remote shack? Sure. Do you want to abuse networking hardware into distributing timing references for SDR purposes? Sure. Do you actually want to sit down and make the video that you said you were going to? Turns out it takes me a little longer to get round to that. However, seeing as we're both here, well, we might as well continue having a look at this Boudica board. So today we're going to have a look at the IF strip, so sort of everything at the down-converted 28 MHz, and see if we can get that going. So, over to the computer to have a look at what we're doing today. And here we have the sort of basic elements of our transverter. So we have our antenna receiving our signals at, let's say, 438 MHz, and we've got our radio wanting to receive it down at 28 MHz. Now the base of our transverter is going to look like this. So coming in from the antenna on receive, we're going to have an LNA, a low noise amplifier, that we'll talk about in a future video, and a PA. So this is your receive path, this is your transmit path, sort of switching those in. Then we'll have our filter, our mixer, so this is the thing that actually does our conversion. So it'll be 438 MHz here, and 28 MHz on the way out. And then we have bit of additional gain on receive, and very little on transmit. Now there are a few more filters and stuff in here, so filter here, but this is the basic block diagram. What we're going to look at today is we're going to have a look at sort of all the 28 MHz section, so all of this bit, and we're going to ignore the switches because we also use those at higher frequencies, and we'll probably be better measuring all those in one go, and it's more likely they have an effect on high frequency performance rather than down at 28 MHz. So let's go over to the schematic and have a look. And when you start designing a sort of complicated system with multi-parts like this, I find it's really helpful before you start digging into schematic and all of that to have a spreadsheet. And what this allows you to do, you can stack the components one after the other and see what it does to the sort of cumulative gain. So that is the gain referred to the input. So see how it progresses through your system. You can check signal levels to make sure you're not overloading anything. And more interestingly, you can have a look at cumulative noise figure and cascaded third order intercept. Now if your third order intercept doesn't mean much to you, go see my previous video. But what this allows us to do is it can show us which parts are dramatically affecting our performance. So you can see here we get a final cumulative noise figure of 0.69 dB, but where does most of that come from? Well, nearly all of it comes from this filter and this LNA, so we need to be really careful about noise figure here, and as we get further to the right the components have less and less effect. The reason for this is, as we discussed in my noise figure video, the more gain you have in front of a stage, the less the noise figure matters. Likewise for third order intercept, what matters is as the signal gets bigger, that stage is more likely to contribute third order products because you're probably operating it closer to its third order intercept point. And likewise here, so you can see this can only decrease, the system can only get less linear, and you can see that, you know, it starts ridiculously high. That's because we've put no parts with any sort of sense of non-linearity, and you can see that it's ultimately set by the step that actually sets the final level is this post-mixer amplifier. So this stuff before is importance, but this is the thing that is setting our ultimate IP3 of this thing. So we should probably optimize this part for third order intercept, which is convenient because at this point our noise figure is now less of a concern. So for this RX chain we care about noise figure over here at the left hand end, and we care about IP3 at the right hand end. But yeah, this is a really useful tool, and it can spot sort of traps before you start going to all the trouble of converting it to a schematic. So let's go have a look at that. Okay, so here's our filter. So this is our TX out from our radio, and going into our switch before we hit the mixer. So we have this attenuator and a filter, ESD diode, a couple of blocking caps, that's about it. In terms of how this was designed, the attenuator is pretty straightforward. I just have a table of all the different attenuators and resistor values, and sort of picked one that gave reasonably nice numbers. Alternatively, you can get sort of online calculators, such as this one, where you can just type in the numbers you want and sort of play around with the attenuation until you get resistors that seem sensible. In terms of how I design the filter, for filters at sort of these low frequencies where we're going to be doing it with lumped components, I tend to use this program called LC. And you can see here we've put in a capacitor input low pass, so looks something like this. And we've gone for Chebyshev. Now those will give us sort of fairly fast roll-off in the frequency domain at the expense of a bit of ripple in the passband in both amplitude and phase. Yeah, other types of filters exist, the two common ones being Butterworth, so that has a flat amplitude response in the passband, but a sort of slower corner, it takes longer to roll off. Or there's Bessel, which gives you the best time domain response, but very slow roll off. So for this, we just want to attenuate everything as fast as possible. And you can see here, we expect a passband ripple of 1/100th of a dB, so that's not going to be noticeable at all. And we'll have that just to remove the outer band signals. The ripple bandwidth, so this is the corner frequency at which that filter starts rolling off, so sort of this frequency here. I played around with it a bit, just mainly to give me nice component values again, and 31 MHz seemed very reasonable. So this thing gives us a schematic that looks something like this. And the big thing I aim for when doing this is I try and get the inductors a nice value. You know, if the capacitors are something a little bit weird, then we can put several in parallel. Capacitors are cheap. You know, it's not too difficult, and there's a wide range of them. Inductors tend to be fewer and further between, so you can see here I was shooting for around 330 nanohenries. So what I tend to do now is I tend to fairly lazily map each one to its nearest single value to see if that's causing me any problems. So I'll do that, and then we'll have a look at the response. Okay, so there we go. I'm generally happy with all of these. The only one that I've made a fairly significant change of this was like 162 puff, and I've upped it to 180, but we'll see as a starting point. Okay, so here we've got our response. We've got our S21, so our insertion loss in blue. It's looking good, you know, no visible ripple, but you'd expect that with only 1/100th of a dB. And our sort of S11 is looking good, you know, it's somewhere here-ish, so we should be shooting around -25, -26. So that all looks excellent. And if we measure anything significantly differently, I'll probably start by looking at that middle capacitor being a little bit off. Okay, so we're all ready to do our measurement. So I've got two ports connected up to the VNA. So what the VNA is doing is treating our system like it is a black box that has two ports, so port here, and will tell us things called S parameters. Editing down here just quickly for a brief on S parameters. So what it allows us to do is to model our device under test, or our DUT, as a thing just having a couple of ports. We don't care what's in it, it's just a mathematical way of expressing the transfer between the input and the output. And we often write S parameters as a capital S subscript 2 numbers, e.g., you know, S21, S11, etc. And what those are is it's the magnitude of the wave travelling out of port X, so the first number, relative to the magnitude of the wave going in at the other. So if we have S21, it's how large the signal is coming out of port 2 relative to it being injected in port 1. Now there are some conditions on this, that all ports must be terminated with their appropriate impedance, blah blah blah, but it's basically a transfer of what comes out one port relative to another. So if you see SXY, it's what comes out of port X relative to what goes in at port Y. And likewise, because waves have directions in which they travel in, we also have the concept of S11, which is how much comes out of port 1 relative to what you put into port 1, i.e. how much power gets reflected at the inputs of the device. Now we know devices will reflect power if the input load presented here doesn't match the characteristic impedance of this transmission line. So normally for RF, if that's 50 ohms and the Z0 of this is 50 ohms, then S11 will be 0. There's no reflection. For any criteria where this isn't met, you know, you will get some reflected energy coming back out this port. So for our sort of standard 2-port amplifier, we'll have 4 parameters. We'll have S11, S21, S12, and S22. S11 is our input return loss, so the reflection here on the input port. By convention for amplifiers, port 1 is the input and port 2 is the output. S21, what comes out of port 2 compared to what goes in port 1, well that's just the gain of the amplifier. S12, this is what happens to the signal trying to travel backwards through the amplifier like this, and we call that its isolation. Now normally for an amplifier we want this to be low, however, you know, because we haven't actually specified what this device is, it's just some generic thing. You know, S12 could be a perfectly important parameter if the DUT was something more than an amplifier, and S22 is your output return loss. So how well matched this port here is to the transmission line it's feeding, assuming again that Z0 is some well-known number, so for all our systems will be 50 ohms. These are what we're going to plot on our VNA, and the two main ones we care about are these two. You know, how much gain does it have, and how good a load is it presenting to the thing that's feeding this? You know, there might be another amplifier coming into this, or something else. So S11 or S21 are the main ones we'll care about. Maybe S22 as well. Normally for an amplifier, S12 isn't a big problem. You know, it's not a desirable feature. We're not relying on it to block signals, because hopefully we shouldn't have a lot of reflections. But anyway, right, back to the measurement. So we've got these set up, and the VNA is calibrated. So let's go over and have a look. And you can see that generally this matches our simulation quite well. You can see that we've got somewhere in the region, looking at the markers, of 4.2 dB. Given that there is an attenuator, which had a theoretical value of 3.2, bit of loss from the filter, bit of loss from the connectors, that all sounds reasonable. So that is the green trace, and the blue trace is showing us S11, so our reflection, what we call return loss, and you can see we're getting sort of somewhere in the region of better than minus 20 dB, so that's perfectly acceptable. So our filter's working well. So here is our receive output from the switch. So all this filtering and attenuator is exactly the same as before. The only distinction is we also have this amplifier as well, just to boost the signal a little bit more. Now, the reasons for picking this amplifier were mainly that I'd used it somewhere else in the design, but broadly, when I picked it for there, I was using it as a transmit amplifier, and where I care a lot about IP3. And we can actually see in our cascaded IP3 that this part here is still defining our overall IP3. You know, it'll be the lowest of any part, and you can see that this one's actually the part setting it. So it is important that it does have high IP3, but it might be a little bit overkill for what we needed. Now, I confess I was fairly lazy when I picked it. I went to Mouser, went for in-stock parts, picked all the ones with an operating frequency down to 20 MHz, and had a quick look at what I got. This one is a highly specialised integrated part with all sorts of variable gain, which wasn't really what I was looking for. These two are mini circuits, sort of packaged 50-watt amplifiers with a price tag to match, so I wasn't interested in those. These two are differential drivers for ADCs, so given that we're using single-ended signals all through here, these aren't much use to me, which means that the top part for doing stuff at this sort of frequencies gives you this ADL 5536, which is exactly what I've used. Now, looking at the schematic, this is pretty much taken from the datasheet. What we have is the 5-volt supply. We have a jumper, so I can measure the current just going to this amplifier in isolation. And I've got a note here from the datasheet that it should draw about 105 milliamps when it's working, so we can check that to make sure it's working properly. We've got a lot of decoupling at a few different values. This is to ensure that you have a low impedance to ground for RF at all sorts of frequencies. And we need a drain choke, these capacitors shorting it to ground. So this has to present a low impedance at DC for feeding power, but a high impedance at RF. Other than that, it's exactly as before. Only thing is, you know, we've got a few more DC block caps than you'd think strictly necessary, which is true. The reason for 2 is it means I can double up the use of J27, either by fitting one or the other, so I can either use it to measure through here in isolation, or through the amplifier in isolation. So, let's go and have a look at the part. Okay, so I've now reconfigured the VNA to be measuring the IF amplifier, so it sort of sits between these two ports, so sort of input here and output here. I've got the main power supply hooked up, and I've got an ammeter hooked up off screen in series with the supply just to that amplifier, so we can monitor its current. Now, it's important before you start sort of connecting expensive bits of test kit to amplifiers to sort of terminate the input and the output, so put a 50 ohm load on both of these and check that the currents are what you expect first. You can't test RF amplifiers with just leaving the inputs and outputs open or short circuit. Some amplifiers are unstable and will oscillate uncontrollably, so it's important to terminate these anytime you power it up so it's not damaged. I already did this as part of sort of pre-video testing, and I'm happy to, if we have a quick look at our power supplies. So on the left we have our main supply, which is currently off, and sort of in the middle here you have got the current going through these two wires. So let's turn our main supply on. There we go, and you can see we're reading 83 milliamps. Now this is quite an important thing. Multimeters, particularly older ones like mine, have quite a high burden voltage. And what that is that multimeters generally can't measure current directly. What they're doing is putting some resistance in, measuring the voltage drop across it, and then using V equals IR to work out what the current flowing through them is. The problem is that some bits of test kit, particularly older ones, the resistance the multimeter presents is actually not insignificant. From the schematic, this amplifier is meant to draw 105 milliamps, and you can see 83 is quite a bit lower. However, if I turn off the multimeter measurement and then manually up a current range, and by setting it to a higher current range, it will use a smaller resistor value to try and measure it. So in this case, I might lose a bit of accuracy, but the benefit I get is I'm using a smaller resistor. So you can see all I've done is change the range, I've not changed my circuit, but we're now reading 108 milliamps, which is much more like what we'd expect. So, an important thing to watch out for, burn voltage in multimeters. Now if we go over to the VNA, once again, we have S21, so the forward gain in green, and the S11 in blue. But you can see that our gain is looking very spectrally flat, anywhere we care about, and our return loss is looking decent but not wonderful. You know, 10 dB it's fine, it's not great. Now there's two things I'd kind of like to do here. One, the gain is flat up to 100 megahertz, so any extra signals we get coupled in are going to be amplified as well. So I know we've got the low pass filter afterwards, but there's things we can do to the actual amplifier itself to reduce the amount of high frequency gain it has. And I'd also like to have a look at why the input return loss is a bit poor. So let's go over to the datasheet and see what we can do. Now looking at the datasheet, it seems that the input return loss we measured was entirely reasonable. You know, S11 is this blue trace, and at about 28 meg it is somewhere in the region of 9.5 dB. We measured about 9.2, so that sounds entirely practical. Now, while I'm not particularly happy with 9 dB, I'm going to change some stuff on the output of the amplifier to try and do something about its high frequency gain. And changing the output condition of an amplifier can sometimes affect the input impedance it presents, so I'd hate to fix the input impedance and then break it by fiddling with the output. And the reason I want to fiddle with the output is that this amplifier is datasheet says it has 20 dB of gain all the way up to 1 GHz, which means if we do nothing about it, it's going to be amplifying all sorts of signals. You know, 433 meg would be sort of car unlockers. It could even be amplifying any sort of leakage of our 400 meg signal that we're trying to receive, so 77s, but there's all sorts of stuff in here that it could be picking up that our SDR then has to work on rejecting. So I'd like to try and roll this gain off. So what can we do about all this excessive high frequency gain that's undesirable? Well, we'd like to add some sort of band pass or low pass element to our circuit. And we can achieve this by adding an extra capacitor in and putting it about here. Now what does this do? Well, remember how I said that this node, all these capacitors present a really low impedance to RF, so this node effectively looks like it's grounded. So from the perspective of any RF, the output of the amplifier looks like this, where this is our drain choke, and this is this new capacitor that we've added. Now 82 picofarad is just a value I've copied over, it's not necessarily the right one. And then our output comes from over here. Well, an LC in parallel is a resonant circuit, and a parallel resonant circuit will present high impedance at frequencies where it is resonant, and will present a low impedance at other frequencies. So we can use this to short high frequency signals to ground. You know, this capacitor will short high frequency signals to ground, and at 28 megahertz-ish, you know, this parallel resonant will look high impedance and have no effect on our signal. So that all sounds rather good. And we can just open a calculator and do the maths. So the frequency we want is 1 divided by 4 times pi squared times f squared, which is 29 megahertz, times 470 nanohenries. Now I did have a check, the tolerance spec on the inductor I've used is sort of plus minus 5%, so should be pretty good. And you can see here that to get it resonant at 29 megahertz, we want a shunt capacitor of 64 picofarads. Now, although we've calculated 64 picofarads, I'd rather that this circuit was operating below resonance in our passband. You know, our passband can go up to 30 megahertz, and we don't want to be right on the edge just in case there is component tolerance. You know, the frequencies where we're wanting this to take effect are far away from resonance, you know, 100 meg plus. So I'll round this down to sort of 56 picofarads, and that should mean for all component values, you know, this is operating below resonance where we want it. Now, using this sort of style of parallel LC shunts tends not to give you amazing close-in rejection. You know, you're going to have to be quite a long way from resonance before you see a significant reduction in gain of this amplifier, but it should help. So I'm going to go put a 56 picofarad shunt capacitor and bodge it in here, and then we'll go and remeasure our performance. Okay, well that didn't quite have the pronounced effect I was hoping for, so in green it is with the capacitor and blue without. You can definitely see we're getting some roll off. What I might just try quickly is take the part off again and redo this measurement. Instead of going from 9 kHz to 100 MHz, going from say 9 kHz up to a couple of gigahertz and seeing if there is any decent difference there. Now, having recalibrated and looking at the span of up to 1 gig, you can clearly see the difference. The green one is without that capacitor, and the blue one is with. So you see here, this is quite interesting, and why I adjusted the output first, in that by adding that capacitor, my input return match has actually improved to somewhere in the region of neg 15 dB. One other trick I possibly could try is this inductor was spec'd in the datasheet to give good performance up to a gigahertz, but that probably means that it's actually not looking that high impedance at the 28 megs we're using it. We're using it right at the bottom of our frequency range, and it's probably the thing setting our low frequency cutoff. So one thing I could do is, if I could make this a lot bigger, well, it's self-resonant frequency, so the resonant frequency formed by the inductance and the interwinding capacitance that is naturally present. Well, if I could make the self-resonant frequency very low, then the capacitor that's effectively in parallel with this, the parasitic one, would allow high-frequency RF to sort of jump across here as that capacitor starts to conduct, and then short it all to ground through this lot. However, in looking at that, I wanted to try that, but the only inductors I can find that substantially increased the inductance had significantly higher DC resistance, which, as we saw from our burn voltage on our multimeter, is a much bigger problem. So I think I'm going to leave it as is. And I set it off to measure the IP3 of this part, so running my automated test scripts, and you can see here that at 28 MHz we get this value of about 37 dBm. If we have a look, swept over a little bit of frequency, you can see there's this strange jump in here, but this is unfortunately due to a rather irritating problem in that this is the true line that should be extrapolated with a gradient of 3. However, when this amplifier goes into compression, it seems that the third order products grow faster and then settle out at another gradient of 3, and I really struggle to make my code separate these two. So the true number is these higher ones, and you can see that we're getting somewhere in the region of 37. Compared to the datasheet promises 39. But, you know, this is taking a single point and extrapolating it. I'm doing something slightly more exact. So, you know, we're fairly close. And there's not actually a huge amount we can do. You know, in terms of what we can change, well, the normal things that can improve linearity are we can run the device at a higher voltage, but this part is fixed. We can up the bias current, but this device is internally biasing itself. There isn't a separate bias pin where we can control to set the current. The only sort of trick I have up my sleeve is I do have a different drain choke. So the part used in there is an 0603 LS, which is the recommended datasheet part. There is the 0603 AF series, so also from Coilcraft, that has slightly lower DC resistance. So I'm tempted to quickly swap that out and see if that does anything. However, I'm perfectly happy with the performances we've got. Okay, well, I'd say that's pretty telling. In the red we have the replacement inductor, and you can see it's somewhere in the region of 1 to 2 dB better all across the board. Now, I'm putting this down to the lower DC resistance. It's about half, so LS is about 600 milliohms and AF is about 300 milliohms. So I'm guessing that means we have slightly higher bias current, and as I said, that increases your linearity. Now, I have checked as well, it's had virtually no effect at all on the frequency response as expected, so I'll take this as a win and swap that part out for the next revision. One thing I would just like to have a quick look at before I close the video is the power consumption of this amplifier. Now, we saw that the bias current was in the region of 105 milliamps at 5 volts, which is nearly half a watt. Now, while this is giving us good performance in receive, When we're in transmit, we don't really need it. You know, the amplifier's just sat there wasting power. Now, so I'd like to try and turn it off. So what I've done is I've hooked up this circuit here, and what this is doing is it allows me to electronically switch the supply to that amplifier. And what I've got here is this is coming in from a signal generator, so I'm feeding a constant 28 MHz signal in here. This is an output going to the oscilloscope. Now it's important to note there is a 50 ohm terminator just under this cable. It's a bit difficult for you to see, but that's important because the amplifier expects a 50 ohm load and the scope has a 1 mega ohm input impedance, so need that to correctly load the amplifier. And I've got this extra scope probe sitting on the switched 5 volt rail, and I'm switching it with this green wire here is coming from a signal generator at putting a kilohertz square wave onto that switch, so we should be turning it on and off at a rate of about a kilohertz. So if we go over to the oscilloscope, what we see in yellow is the RF signal, after that attenuator, and what we see in green is the voltage on that switched rail. And we can see a couple of interesting things here, not least of which is that fairly substantial spike. You know, that spike is 1.5 volts in amplitude through a 10 dB attenuator, so 10 dB is about 3 times in voltage, so that's nearly the entire supply. So that's pretty serious and runs the risk of seriously damaging any downstream radio that's receiving this. So we need to do something about that. The behaviour on the turn off, I'm kind of less concerned about. At the point it's turned off, I'm not using it, as long as it's not doing anything dangerous. But I think I'd like to do a bit better on both of those. You can also see that the switched rail isn't completely discharging. You know, it's only going down to, we're on 5 volts a division, so it's only going down to like 1 volt. So let's address each of these in turn. The most important one is that massive positive going spike on the RF signal. You know, that's going to damage something. So what I propose we do is we slow down the slew rate on this rail. You know, that's turning on incredibly quickly. We're doing 1 to 5 volts in somewhere in the region of a few hundred nanoseconds, which is incredibly quick. So we can use the capacitor to slow that down. And here's the circuit I propose to do this with. So we had this sort of PFET before that was switching it in, and a 10k pull-up, and the addition of these 3 components is what's going to help. What this means is the addition of this R4 means it takes time to charge and discharge C1, and you can see that instead of V out switching quickly, we now get this much slower rise time. And by reducing the rise time, that's probably what was capacitively coupling to the output, because we saw a 5 volt spike, so it's probably just the rate of change of the input voltage. So by slowing this down, you know, this now has a frequency of 13 kilohertz. I'd pay very little attention to that. These FETs are just random parts that I've picked. But, you know, it's getting us into the territory of that our amplifier will be fast enough to respond to it, and it should be at low enough frequency that it won't couple through to our radio. So I'm going to go do that mod, and we'll have a look at those waveforms again. And after that mod, with the scope on exactly the same settings as before, this is looking much better. We now have to sort of reduce the time base a little bit so we can actually see everything, but there's absolutely no overshoot there from the intended signal level. And that's true on both the rising and falling edge. So that looks a very worthwhile mod. So once again, we'll add that in, and now we're able to switch this switch in and out on transmit and receive. Last thing we should just record for posterity is the time taken, so you can see that the first cursor comes in, you know, somewhere around there, and that our RF signal has reached its full amplitude, say about there. So we probably need to leave about a millisecond between turning this amplifier on and using it. So that's a useful figure to know when we start looking at transmit-receive sequencing. But other than that, I'm calling the IF stage complete. Well, I think we've made some amazing progress today. We've validated the performance of a whole chunk of the transverter and made some notable performance improvements upon the initial design. Anyway, that's all I've got for you today, so thanks very much for joining me. Any feedback welcome, either in the comments section or on Mastodon at M0WUT. Otherwise, thanks for joining me, and 7-3.